Hello, this is Physics 1C for April 7th, 2020. These are the topics we're going to be discussing today. The first thing we're going to talk about is an application of something we learned last time. Just to refresh you on what we did last time, we talked about how there's this thing called the magnetic force, and the magnetic force is given by a charged particle's charge multiplied by its velocity. And then you have to take the cross product with B, where B is a magnetic field. And you can use something called the right-hand rule to show that, or to see that the velocity, the magnetic field, when you take the cross product, you get a vector that is at a right angle to the plane that contains those vectors. And the way that ends up working out is like if a particle has a velocity this direction, and if there's a magnetic field vector that points off in this direction, and then we say that, those particles, these guys are like in a plane, which we could maybe like kind of draw a plane and say, okay, this is the plane that these objects are in here. Then the magnetic force acting on a particle, it needs to have charge too. So we'd say there's some particle here, and it has a charge Q. Then, do you guys remember what direction would the force on this particle be? Imagine that that plane is kind of coming out towards you or something like that. What would the direction of the force on this be? Yeah, that's right. It would kind of be down this way and then kind of go below the plane like this. That's force. And you get that by pointing your fingers of your right hand in the direction of the velocity vector and then rotating them towards B. So you rotate from there to there, and the direction that your thumb points should be down. That's the magnetic force that we learned about last time. We discussed some applications of this, such as the velocity selector, a mass spectrometer, and the last application we're going to talk about today is a cyclotron. This is not something that your book talks about, but I think it's a really fascinating thing that is at least worth describing to you guys how it works. So this basically works like this, and I think I'll use a circle tool to actually make this look kind of better. So you've got a circle, okay, and we're going to cut it in half by using this tool, I think. Try to break the circle exactly in half. Oh, it selected that thing inside of it. Let me make sure there's nothing else for it to select. So we're going to cut this circle in half. Ooh, it really doesn't want to do that, does it? I have to do something like, I bet because it's an object, it won't let me do this. Well, that's okay. We'll just do this. So, here. Small eraser. So if we just cut a hole out of here, and cut a hole out of here, and then we draw a line, and we're going to try to draw a line straight down. Nope. Do as best I can to draw a straight line here. That way, and then this way. That's fine. That's good enough. So we've got these two, what are called D's, like one D that points to the right. You can see that looks like the letter D, right? And one D that points to the left. Okay. Now each of these is a metal plate. Here. So each of these is a metal plate, and you connect it to what's called an alternating voltage source. And I'm going to draw a little symbol for that here and describe what it does. So what this little thing right here is going to do is sometimes this side's going to be positive and sometimes this side's going to be negative, but it's going to basically flip it back and forth, positive, negative, positive, negative. And then each of these guys is a metal plate. In between, you have an air gap. Oops. Gap. And then these plates will be held at different potentials, okay? So one's going to be high potential and one's going to be low potential, right? So let's say in this configuration that this side right over here starts off as the high potential side. So this is the high V, and then this would be the low V plate. In addition, the entire thing is going to be embedded in a magnetic field. So there's a magnetic field that's going to be kind of, let's say, pointing into the page like this in the entire region. It's a uniform magnetic field. So there's a lot of X's to represent that there's a uniform magnetic field all throughout the region, including in the center. And again, I said last time the way that you do this, but the idea would be that if you put the north end of a magnet above this, like looking down, and the south end of a magnet below it, then what you're going to get is something like this. So you can imagine if we tilt this as like a side view, or an edge view might be a better way to say it. So if we look at the edge, like if we look at with our eyeballs like this way, and we're looking up this way, And the edge view of this is going to be like, okay, we've got our little D's right here, right? Separated by a gap. This is your high voltage plate. This is your low voltage plate. And then in order to produce that magnetic field like we have right there, all we need, see if I do this right, you need the north end of a magnet here. So you've got some kind of a magnet, and this is the north end. And then you just need the south end of another magnet here, or you can have the same magnet if you want to. And what that does is it creates these magnetic field lines that go from north to south, right? That's the direction of your magnetic field. I never even labeled that, but this is the magnetic field in this picture, okay? So hopefully you can envision how you might produce something like this. That's certainly not very hard. It's easy to find metal plates, okay? So now the way this ends up working is like this. Gotta think about this. So this is low voltage and this is high voltage, right? So if I were to place, right at this location here, kind of near the center, a charged particle with some charge that we call Q, right? And I put it on the high voltage plate, then what's going to happen is it's going to get a kick of energy, right? And it's going to end up over on this side over here, and it's going to have an increase in its speed, or an increase in kinetic energy. That will be equal to, what would it be equal to? If this plate is at some voltage and that plate's at some other voltage, and the gap between the plates produces a potential difference that we call delta V, then how much kinetic energy is this object going to gain? Let's say it starts from rest right here, and that it gets over to here. How much kinetic energy does it gain? Does that question make sense to you guys? What's the increase in kinetic energy as the object goes from V equal to 0 over here, and when it's going to get over here, it's going to have some kind of speed, right? Yeah, that's right. So it's going to pick up some velocity here, right? Oh, it looks awful. Okay, it picks up some velocity there, and the increase in kinetic energy should be equal to the potential energy change. So that's going to be equal to Q times delta V. So you can basically say this is going to be equal to 1/2 m times v squared, and you can even figure out what the velocity is at that location, right? So basically, the way we think about this is that as it goes between these points, it gets a kick of energy. Does that make sense to you guys? It basically gets its velocity stepped up from 0 up to some value. Does that make sense? Okay. Man, I just realized looking at this is going to be a little harder to do than I wanted. Well, gotta stick with it. I'm going to do one thing real quick here. Let me see if it'll stroke erase, and I can move this up a little bit. No, not that. I just want this one. Nope, they're all connected, aren't they? Rip. All right, we're going to have to do some cleaning up here, because we're going to run out of room if I don't. So same idea, but I'm just going to move up these, like where the object is real quick. Should be able to get this picture back to looking kind of okay. Where is blue? Blue. Okay. Fix this line. This line. Now all I'm going to do is I'm just going to move where the particle was, and that might not seem like it matters, but it will matter quite a bit. So our particle starts off right here. It has a charge Q. It starts off with a velocity equal to 0. It gets a kick of energy, gets over to this location here, where now it's going to be moving with a very with a higher speed. Okay, so it's going to pick up some speed over here. It's got a velocity like this. So now you guys tell me, what's the direction of the force on this particle now due to the magnetic field? What's the force on the particle due to the magnetic field? What direction is it, I guess is what I'm asking. What's the direction of the force on this particle at this point due to the magnetic field? It's down, right? So we've got a force on this particle, and it points downwards. So that means the path that this particle is going to travel along, here, I'll label it, that's the force. I'm just going to say F like that. So now the path the particle is going to travel along, what kind of path is it going to travel along? What happens when I have a magnetic field that goes like this, and I place a charged particle in it so that its velocity is this way, right? It feels a force that's up. So what kind of path does it travel along? Circular path. It's going to go around in a circle kind of like this, right? That's exactly what this guy's going to do. It's going to go around in some type of a circular path until it gets back to here. Now, when it gets to this point, if nothing else changes, it's not really going to be able to do anything because the positively charged particle doesn't want to go uphill, so to speak. It won't go from low potential to high potential in the same way that a ball would never roll up a hill by itself, right? So what happens then is that the low V and high V swap. So basically, what was originally low potential, now basically that's not going to work like I want it to work. So basically, this one now is going to become high potential. So we're going to swap this. We're going to make it so that what was originally negative is now going to become positive. So now this one's going to be positive over here, negative over here. This is going to end up being the high potential now, right? Because it's the positive side. And the other side will end up becoming the low potential side. Does that make sense? So now we just say this is going to be the low potential side. And then what happens is the particle is going to get another kick of energy as it passes between these 2 points. So its velocity is going to increase as it goes from here to here. And now it's going to come out of here with a larger velocity, right? Because it's going to have another kick of energy, right? Each time it goes between the gaps, it's going to get that same kick of energy, having the same velocity increase, right? So, not the velocity increases the same, but the energy increases the same. So now what's going to happen is it's moving faster, right? And now this is worth like going back to something we learned last time. We learned last time that in the situation like this, if you define the radius of the path to be r, the radius is mass times velocity divided by charge times magnetic field. That's one of the things that we derived last time, right? We also derived that I think omega, which is the rate at which it cycles through the system, is equal to qb over m, I think, right? This one is independent of velocity, and that's really important. This one's not. So the radius of the path that it travels along is dependent on the velocity v. It's also dependent on mass, charge, and magnetic field, but these other things are not going to change, okay? The velocity increases. What happens to the radius of the path if the velocity that the particle has when it gets to this place right here, now the velocity is bigger, right? So what happens to the radius of the path? What happens to the size of the path? So this was the size of the path before, this little circle right here. Semicircle. Is it going to get smaller or bigger? It gets bigger, right? So now the path that it travels along is just a bigger circle, right? And that's going to be something maybe a little bit like this. And then it gets to here again, right? And so what has to happen now if it wants to get another kick of energy? It doesn't want to go from low to high because it's a positively charged particle, right? So what has to happen for it to get another kick of energy between these 2 points? Yeah, exactly. So now we swap these. This becomes, and this guy here, right? So now it swaps again. You may be wondering how this happens, and I'll tell you exactly here in a second. So we need this one to be plus now, right? We need this one to be minus. This will be high. This will be low. And it'll get another kick of energy, right? So now it gets a kick of energy. See, this is what's cool about this. Like, every time it passes through here, it kicks a kick of energy, and now it has a bigger speed, so it goes in this wider circular loop right here. And you can kind of start to figure out what's happening here pretty quickly, right? It's just going to keep going in these circular paths that get bigger and bigger and bigger, right? The spiral just gets bigger and bigger and bigger. And eventually, you might want to, like, let the particle escape or something. I don't know. But what's happened here is you were able... I forgot to say, this is called a cyclotron. You're basically able to increase the velocity of the particle to any amount you want. Like, you can speed up any charged particle by doing this. And then once you've sped it up, you can send it off to do other things. But that's the idea of a cyclotron. You can basically have this location where you accelerate particles, just using the principles of the way that the magnetic force works, the way that the electric force works, potential differences and stuff like that, right? Okay, does this all make sense to you guys so far? This is what we call a cyclotron. This is what we use even to this day to get particles up to really high speeds. So we can use them to investigate properties of matter, because one of the ways in which you can investigate what things are made out of is to take particles moving really fast and fire them at the object you want to study. That's how we probe things. That's how we learn about what they're made out of. That's how we learned that protons are made out of quarks, because we fired really, really high-speed electrons at protons with the goal of literally destroying them, of breaking them apart into their constituent parts. Does that make any sense to you guys? You take a solitary proton, actually take a whole bunch of protons, and then you just bombard it with really high energy electrons. And the effect is that out of this, what can happen is that the electron can, if it's a high enough speed at least, it can penetrate the proton, and the proton will basically explode, and the proton will explode into quarks. And I'm not going to go into the details of what goes on there, but the point is that you can basically, you can rip apart fundamental things by doing this. This is something we've always done early on in our studies of the nuclear reactors and stuff like that. The way we were able to split the atom was by using particles like this, by splitting them with high charge particles, except in that case it was neutrons and it was a nuclear reaction. But this is how we study the universe. We just take really high velocity particles and we shoot them into other things, and we look at what comes out of the wreckage. It's about the same as taking a toaster and dropping it on the floor to break it open so you can see what it's made out of or something like that. But this cyclotron is one of the ways in which we can actually accelerate particles to really high speeds. Okay, do you guys have any questions about this? I think this is really fascinating, like how simple this device is. So, based on what I've told you so far, can anyone tell me, how do you make it so that this thing, right, this alternating voltage source here, how do you think we tune it to make sure that it flips the polarity at just the right time? What will we need to do? How can we make sure that it flips the polarity at just the right time? Well, the thing is that the particle isn't exactly going to stop. Okay? Well, I mean, I guess it would eventually, but if you think about what happens when it goes from here and then it goes through here, when it gets to this location, it still has energy, right? In fact, it has just enough energy to cross the gap, right? Because it gained energy by crossing the same gap. So think about it like if I take a ball, right, and oops, that's a bad way of saying it. If I write something like this, this would be the scenario of what's going on here. You take a ball, you let it roll down to the bottom of the hill. Well, now it's got just enough energy to make it back up to the other side, right? And that's when it would come to rest. That's basically what would happen, is it would get to the other side and it would come to rest, right? I don't know if does that make sense to you guys? Okay, so, yeah, what do you think? How do you ensure that the polarity flips just at the right time? And to answer your question, sure, there'd probably be a way to detect that, but there's a simpler way to do it, I guess. Individual charged particles are not only hard to see, they're definitely hard to detect. Maybe I could ask the question in a different way. What if there was a way that you could flip the polarity in a consistent way? Meaning that you could set the frequency of this device right here to some number, right? You could set the frequency at which it alternates from positive, negative, positive, negative. What if you could just set it to a number, like let's say 120 hertz, for example? And you could tune this. You could make it go up to 1,000 hertz or 1,000,000 hertz or whatever you need to set it to, but this was tunable, okay? And actually, to be truthful, you guys have actually seen a device that will do this. The only lab that we've been able to do this semester, you used a voltage source just like this. And one of the things that you could tune on it was the frequency. You can tune it from 0 hertz up to like millions of hertz, okay? You can just, it's tunable. Does that make sense? It's very easy to set this frequency. This frequency of 120 hertz, we'll say 60 hertz is the frequency of the power that comes out of a wall socket, okay? So how would you know what frequency to set it to? That's a different way of asking the same question. What frequency should we set the generator to in order to make this work? Well, so here's the question. Does the period of its motion depend on its velocity? Does the period of its motion depend on its velocity? It doesn't, right? What's the period of its motion dependent on? That's it, right? And we can say, well, we also know that if this is the angular frequency, right, the period is equal to 2 pi divided by the angular frequency. Now, this would be the time that it would take for, so it's what, 2 pi times the mass divided by q times b. That's the period, right? And how long is it going to take to go from here to there? That's half of a circle, right? So it just takes t over 2 as your period. So that's going to be equal to just pi times the mass divided by qb. And then really what you want is the frequency, right? So your frequency is going to be equal to 1 over the period, or 2 over the period in this case, right? So that's going to be equal to qb over pi times mass. So all you need to know is the charge of your particle, the mass of your particle, and the magnetic field in pi, and you can find exactly what to set the frequency of the generator to guarantee that it flips every time that you go through a half cycle. And I think that's really neat. Like, it's completely independent of the velocity, so you're able to just simply tune the frequency here just to make sure, and the tuning frequency, right? It's going to be based on fundamental properties of the particles themselves, right? It depends on the charge of the particle, whether it's a proton or an electron or a alpha particle or something like that, which is a helium nucleus. It depends on mass, and then it depends on the magnetic field, which you can set the magnetic field. We'll learn today, I think, how it is that you would control this factor right here. Because all we have told you guys so far is like what a magnetic field is and how it affects like certain things. We haven't talked about how to produce these things yet, how to produce a magnetic field and how to set it to a specific value, but it turns out that's actually pretty easy to do too. You just use these coils of current. So I don't know, I find this device to be fascinating. It's one of the devices that let us really start to understand the way that fundamental particle interactions occur. And so that's a cyclotron. Do you guys have any questions? Any questions? All right. In that case, let's start talking about the magnetic force on a wire. So I've got a video for this, and then I've got a couple problems that we're going to do. Quite a few problems, actually. Probably do them in this order. Go this one, and this one. All right. So next topic. Okay. Magnetic force on a current carrying wire. So this picture here basically describes exactly what I want to describe to you. So if you have... What's up? Was there a question? So suppose I have a wire, and it's connected from this point to this point here, and we place around that wire a magnet, and the magnet is such that the north end is here and the south end is there, which sets up a magnetic field pointing kind of into the page, as you can see in these three situations. What you can experimentally observe, and we'll see here in this thing, is that if there's no current in the wire, then there's no force on the wire. When the current flows upwards, there's a force that points to the left. So in this situation, there's a force that's pointing this way. And I really wish I could show you a demo of this. I mean, I can show you this video, but I think this is a pretty surprising effect, that if you take a current carrying wire and you put it in a magnetic field, that it feels this big force like this, right? When the current goes in the opposite direction, you get a force like in the opposite direction. The way that you define what this force is you say the force is equal to the current in the wire multiplied by a length vector associated with the wire crossed with the magnetic field, okay? So if we take one of these scenarios right here, like if I have current that's flowing up like this, okay, and I say that the length of my wire, you kind of need a vector for this. So if I say the length of my wire is like that, call that L, that's the length. And the direction of this is in the same direction as the current. Then if I have a magnetic field here, like let's say our magnetic field is coming into out towards you. So this is our magnetic field. So there's the magnetic field B. Then what we do is use your right-hand rule, and you say if I point my fingers in the direction of L, and then I curl them to the direction of the magnetic field, I'm going to get a force in this case that's going to point on the wire to the right. Use a different color for that. And again, you use the right-hand rule for this. Now, the force you define here is basically the total force on the wire, okay? So how that force actually acts is probably going to be on the center of mass or something like this. But that is the force on a current carrying wire. Do you guys have any questions about that definition? It's got current, length of the wire, crossed with a magnetic field. And here's a video of this. Now, how do I just open this on YouTube? If I play it, oh, okay, that works. Whoa. Is it playing? Here, let's watch this on YouTube so we can see a larger version of it. Okay. Can you guys hear the audio, by the way? I paused it, but were you able to? I didn't hear any audio. Okay, what about now? Really? I'm sharing my screen, but it's not playing any audio, huh? What about this one? Was this one playing audio? Why would that not work? You guys have any idea why that wouldn't work? Yeah. Yeah. It's recording sound on the I'm looking at the settings. So it's only sharing the screen, but it's not sharing the audio. But it should definitely be sharing both. Okay, this feels like something I could spend a lot of time on. Maybe I'll look at it during the break. For now, I'll just tell you guys what he's saying, or you can watch the video on your own if you want to. The link is right there in the... I guess right here you can see it. So, okay, we'll watch the video and I'll tell you what he's saying. It's very short. Okay, he's saying there's a large magnet, the field points up. And there's a copper tube. It's connected to a wire. And then he's got a battery. And he's saying that an electric current's going to flow from the red wire in the direction he's pointing. And then up through ground and then back around. So you've got the current that way, the he's pointing. Magnetic field pointing up. Okay, so he's doing the right-hand rule right there, right? As he said, we'll just like show what he did again with his fingers. He's saying that... I didn't go back far enough. The current flowing that way. The field's up. So you can see that his fingers are curling to make it so that his thumb points kind of in that way. So now he's saying if you reverse the direction of the current, the force should go the other way, and it does. It kind of looks like magic, right? You can see that it comes to a balance there, right? There was a point where it balanced out so that the weight of the object was in equilibrium with the force from the... yeah. Okay, hopefully you guys are able to follow that. I don't know, does that surprise you that happens? It does look like magic, right? I'm glad you agree. Okay. I feel like most of electricity and magnetism kind of can feel like magic to a certain extent. So let's investigate how this can work. And our goal here, by the way, just to keep things in frames, like you might ask, like why would we care about this? Why does it matter that these things feel a force? Well, I would say that at the core of all electricity generation in the United States and across the world is this principle right here. This is how we harvest the energy of electricity. We begin with this, and then we'll take a loop and see what a loop feels. So we're just going to build slowly. We're going to start off with a really simple problem right here about the magnetic force on a straight conductor. I'll leave the theory right there, and we'll do this calculation. So you've got a straight horizontal copper rod, and it carries a current of 50 amps. Okay, so that's our current. Here, let's write over here. In this problem, we've got a current that's equal to 50 amps. Actually, do I really need to write this stuff down? All the information is actually basically right there, right? Current's 50 amps from west to east in a region between the poles of a large electromagnet. In this region, there is a horizontal magnetic field towards the northeast, that is 45 degrees north of east. So you can see the magnetic field's going like this in the plane of the page. Find the magnitude and direction of the force on a 1 meter section of the rod. While keeping the rod horizontal, how should it be oriented to maximize the magnitude of this force? And what is the magnitude of the force in this case? So the first thing is to find the magnitude and direction of the force on a 1 meter section. Now, this is pretty easy to do here. Let's define what these vectors are here real quick. So the vector L in this case, right? It's a vector here, so we need to write it as a vector here. It points in the same direction as the current, and the current's going that way. The length of the section that we're looking at is between here and here. It's only a meter long. So we're going to say this is going to be 1 meter, and then we're going to multiply that times the I hat, right? And then for B, the magnetic field B, this one's pointing at a 45-degree angle. The value of the magnetic field is 1.2 Tesla, but because it's at a 45-degree angle, I would say that this could be written as basically, what does it matter, sine or cosine, but you could write this as basically cosine 45 I hat plus sine 45 times j hat, okay? And then we need to do FB is equal to IL cross B. So I is 50 amps, that's a scalar. We multiply that times the length, which is 1 meter. And then we need to cross product that with the magnetic field, which is here, so we'll just copy paste it. If I can get all the things. It's gonna be hard to do because I made it. That should be good enough. Copy paste. So we're taking a cross product. Put the cross back in there. These two vectors here. Oh, and I left out the I hat. So there's also 1 meter I hat for this, and then we're cross producting with that whole vector right there. Right. Now, when we get this, we do I cross I. Can you guys tell me quickly, what is I cross I equal to? What is I cross I equal to? Yep. So we don't need to worry about I cross I term. We only need to worry about the other terms. We've got, what, like 50 amps times 1 meter times 1.2 Tesla, and then times the sine of 45, and then what is I cross J? You can use your fingers. It's K. You can use your fingers to prove this. You point your fingers along the x-axis, right? You point your fingers this way, and then you wrap your fingers towards J, right? You're going from I to J. So you wrap your fingers in that direction for your right hand. Your thumb should be coming basically out of the page right here in the K direction, okay? So all of that times K hat. That's going to be our answer, right? So F sub B is going to be equal to, feels like this should be easy enough to do. Well, I don't know what sine 45 is, like 0.7. This is going to be something, you guys can calculate it real quick if you want to, and tell me what the answer is. It's going to be something like 42, I think, or something. Is that right? Did I do the math wrong? Cool, we'll just call it 42K hat. All right, and I was just like, kind of just doing that in my head, so. There we go, 42 newtons. Pretty straightforward kind of plug and chug vector problem. It's part A. Did you guys have any questions about that? While keeping the rod horizontal, how should it be oriented to maximize the magnitude of the magnetic force? And what will the force be in this case? So how should we orient this rod to maximize the force? The field, right? Yeah, so if the field is this way, then to get the maximal force possible, we want them to be at right angles to each other. So we'd want the current to basically be going in that direction. And then if we do IL cross B, we'll still get K hat, but there won't be any angles because now, so now what we're going to get, the angle between these two is now 90 degrees. It almost makes no sense to write it back out into component form, but we could, what would L become? Yeah, it feels really silly to write this out in component form now because now all we're going to have to do is say FB is going to be equal to I times L times B times the sine of the angle between the two of them. And then it's going to point also in the K hat direction, just like before, because if you do L cross B. So this one I think is going to be 50 times 1 times 1.2, so that should be 60 newtons. Also K hat. Now we could also have oriented the rod, we also could have made the current go this way, and it would just made negative 60 newtons K hat. It would also work as well. Either of those would be fine, but this would be the answer then. All right. Does that sound, does that look okay to you guys? Anyone have any questions? Okay, if not, we're going to do another problem here. This one's tricky. So we'll do, I think, this one first. I think you guys have a problem like this either on this homework or the next one. Well, maybe not exactly like this, but this is the same principle. So here's the problem. A rod of mass 0.72 kilograms and radius 6 centimeters rests on two parallel rails. They're 12 centimeters apart, and the length of the rail, so this is the rail, is 45 centimeters long. The rod carries a current of 48 amps in the direction shown and rolls along the rails without slipping. Does that look like something you guys have heard before? Rolls without slipping? Does that sound familiar to you guys? Yeah, there needs to be enough friction to make that happen. Yeah, exactly. And does it remind you of anything from Physics 1A? You were doing problems like this? All right, if not, we'll talk a little bit about that. A uniform magnetic field of magnitude 0.24 Tesla is directed perpendicular to the rod and the rails. It starts from rest. What is the speed of the rod as it leaves the rails? Okay. This is effectively a mechanics problem, but what's being described here, if you think about it, if you use the right-hand rule, can you guys tell me what's the direction of the force acting on this rod right here? If you use the right-hand rule, what's the direction of the force acting on that rod? Yeah, you should be able to prove that the force is going to be parallel to the rails and it's going to point like this. That's the magnetic force. So it's clearly going to have the effect of basically accelerating that object, right? So what we're going to do here is I'm going to have you guys think about this and see if you can't try to solve it. I would suggest that you should try to use conservation of energy. This is the equation where it's like work done by non-conservative forces is equal to the change in kinetic energy of the object plus the change in potential energy. In this case, the work done by non-conservative forces is going to be the work that's done by the magnetic force, so the work done by B. We're going to not worry about any slipping due to friction, but the work done by this, right, should be something like the magnetic force multiplied by the length. And I'll let you guys think about this. So I'll give you guys a few minutes, like 5 minutes. I want you to kind of work on this and see how you can do. I will say that one of the things you need to remember for this is that if you have a cylinder, the moment of inertia for a cylinder is equal to 1/2 the mass of the object times its radius squared. This is not current. This is moment of inertia. Unfortunately, they happen to use the same symbols. There's not really much I can do about that. Okay, give it a shot. See if you can solve this problem. Oh, and the magnetic force is given right there. Let's zoom out just a little bit so you can see it. See everything. But there's our magnetic force equation right there. Let me know if you have any questions. No. The I represents current. The L represents length. No. There's no I. Where? Wait, where are you talking about?
I thought like the I is a vector. Current is a vector, right?
Current is not a vector. Nope. Current's a scalar. Current density is a vector. Displacement's a vector. Length is a vector. But current itself is a scalar. Because think about that. This current carrying wire here, you can curl it up. Like I can take a wire and I can wrap it in. Anyway, yeah. So current's a scalar.
Yeah, okay. I see what you're saying.
There's nothing wrong with thinking of current as a vector, though. I mean, it does have a direction. Okay, so yeah. that enough time? Do you guys still need time to think about this? How are you guys doing on this? Can I give you guys any tips or anything? Is there any questions you have that I can give you a few hints here to get you moving if you're getting stuck? Okay, that part's. Go ahead. What do you think it's going to be? Yep. Well, this force is a constant force, right? So you can just do F dot delta R if you want, yeah. You don't need to do an integral because it's a constant force. So the left-hand side is just going to be the force, which is basically just I times L times B, and then you need to multiply by the sine of the angle between L and B, which in this case is going to be what? 90 degrees. That's the left side. That's all there is to it. Oh. In this case, actually, it's D is the length here, isn't it? So this should be I times D times B. My bad. Yeah. Okay, what about the right-hand side? What do I need to write down for the right-hand side of this equation? Is there any change in potential energy? Are there any springs? Does it go uphill or downhill? Yeah, so this part's 0. There's no potential energy associated with the magnetic field. Kinetic energy, this object is rolling without slipping, right? That means that it's going to have your normal kinetic energy, 1/2 mv squared, where this is the velocity of the center of mass of the object. What do I have to add to this if it starts to roll? What's the other term? What's the term for the rolling kinetic energy? It starts with a 1/2. Does anyone remember what it is? Yeah, that's right. And to distinguish this I from that I, I'll put I cylinder right here. Now, what's the relationship between Vcm and Omega? How is this one related to this one? Yeah. Yep, that's right. Okay, do you guys think you can solve it then? You should have all the information you need to get an answer here. So I'll give you guys a few more minutes and see if you can't solve it. Does stuff look familiar for you? This thing that I just wrote over there is the condition for rolling without slipping. If you didn't, I assume you guys all covered this in 1A, right? You must have done problems where there was rolling without slipping. Is that right? Okay, good. I'll see if you can solve it. Do you want to already get an answer? If you get an answer, put it into the general chat, and that way people can kind of check. You know, give it a shot. See if you can't solve for. We're looking for the speed, right? So you're looking for velocity. This R, by the way, is the radius. Okay, this is the radius of the cylinder, right? So if you have a cylinder, so there's your cylinder. R is the radius of the cylinder. Now that's not given in this problem, right? But it will cancel out of your calculations right here. So, yeah, what J-Box said, Vcm divided by R is what omega is. That's exactly right. There was a question about how you find B. It's 0.24. Yeah, it's hard to see that because it doesn't like say B equal to, but yeah, it's the magnetic field. Yeah, write down your answer what you said just now into the chat, and then we'll all see if we get the same answer. And then the mass is 0.72. 1.31. Anybody else get the same answer? Flash Player will no longer be supported after December 2020. Why is that? What's going on with Flash Player? Is it being upgraded to like HTML5 or something? Anybody else get an answer? What was mass? The mass is right here, 0.72. I got 1.6. Okay, cool. It's exactly 1.6, which means that all of this is somehow equal to exactly 256. I mean, you can see that a lot of these things have common measures, like 48 over 3 is 16. And then, I don't know, yeah, 0.24 over 72, those are related to each other too, right? 24 and 72 would be like 4 over 12, it's like 1 over 3. So 1 over 9. What? How does this end up being, whatever. Somehow it ends up being exactly 1.6. Yeah. Oh, I didn't put L on there? You're right, I didn't. I also changed the symbol for L. I'm sorry about that. Good point. Good point. This one was doing a different color so I can indicate the mistake that I made. That's L. And L was equal to 45, right? So this is multiplied by... Yeah, so that's not the right answer. This is going to be times 0.45. Thank you very much for whoever noticed that. I really appreciate that. And then this guy... Whoops, to erase this. You're saying you now get 1.07? Cool. .07. Good. Okay, that's really good. You know, this is actually... They call this a railgun, right? Because you basically have rails, and it has the ability to accelerate an object, right? I'm pretty sure that recently I heard that on aircraft carriers, this is one of the ways that they launch planes to get them up to a really high speed without using the jet engines. Is they, I mean, they use the jet engines, but they want to be able to like get them up to a really high speed very quickly. And so this is one of the methods by which they do that on a much larger scale. Because if you're accelerating a plane, you've got this huge mass in the denominator here, so you're going to need to have really big field, a decent amount of length to work with, but that's limited on an aircraft carrier. Yeah, so anyway, it's one way to produce a projectile, to speed something up. Devices like this have been proposed as ways to send people to space too. Create a really long rail and basically accelerate the object using electricity instead of accelerating the object in the normal way we get things into space, which is through rockets. And yep. Anyway, so kind of one of the applications of the electric force. Or the magnetic force. Do you guys have any questions? Probably should take a break here. It's been an hour, so we'll start again until 15. Maybe there's a question, so I'll wait a second. Why call it a railgun? Well, it's because you've got these rails here, and the idea would be you'd make the rails really long, and then it would accelerate as long as it was on the rails, and then, basically the object rolls along the rails. And it's kind of like a gun, I guess is why you'd say railgun, is because then you could imagine that you project this object out. It's kind of the idea. You could call it a rail accelerator if you want. Friction is neglected. Now, so here's the thing. There would be friction in this system, but commonly when we look at problems where we're talking about the object rolling without slipping, then it's not... How to put this? We're not really neglecting friction. There's another way to do this problem where I put friction into it, okay? And, yeah, do you want me to show you real quick? So if there was no friction, the object would just slide along the rail, right? That'd be one way to do this. You could just have no friction. But the other way to do it would be to consider how the forces are actually acting on the object. So the magnetic force that acts on this object, now I'm looking at this from this end right here, okay? Then the magnetic force is going to act from the center of mass like this, okay? This actually isn't going to make it roll, okay? Because the magnetic force would be equal on both parts. The current is coming, out of the board, right? So we have like a current here and we have a current here. So you can imagine that this magnetic force, it really only has the effect of making the object slide, because the force acts here and it acts here equally, right? That force can't actually make the object roll. So why does it roll? Well, it rolls because it's on a rail and there's just enough friction to make it roll due to a frictional force that acts down here, going back this way. That's our friction force, right? Now, we don't have any information on the problem to actually calculate what the friction force is, right? But what we do know is that if we sum up all the forces acting on our object, that it should be equal to the mass of the object times its acceleration, right? So in this case, that would be the magnetic force, which we know how to calculate, minus the friction force, and that would be equal to the mass of the object times its acceleration. Now, this wouldn't be enough information to figure out what was going on, because while we know what the magnetic force is and we could then use it to find acceleration, we would also need to know something about friction, which again, like, we don't know what the coefficient of friction is, for example. We just know that it rolls without slipping. So then in addition to that, what we can say is, well, the object is actually going to accelerate in this direction. It's going to have an angular acceleration that we call alpha. And if you remember something that you may have learned at the end of 1A, if I add up all the, not forces, my bad, if I add up all of the torques acting on my system, the sum of all torque should be equal to the moment of inertia of my system multiplied by alpha. The torque, now you pick whatever you want for your torque, right? But normally we would choose, in this case, the center of the object to be our axis of rotation here, about which we're going to define torque, in which case you would only have the force F multiplied by R to give you torque. Now we know that I, we said, was 1/2 the mass of our object multiplied by its radius squared. Well, the radius squared is the same thing, R, that shows up on the left-hand side. And then that's multiplied by alpha. Now I'm going to go through this kind of fast because we're going to take a break and I can say more about it if we want to. But the condition for rolling without slipping is this, or that the same thing is true for the acceleration, which is that alpha should be equal to the acceleration of the center of mass divided by the radius of the object. So that shows up right here, right? This is technically acceleration of center of mass, acceleration of center of mass. So what we can do now is we can replace alpha with the acceleration of the center of mass divided by the radius, okay? And then this equation simplifies down to one of the r's cancels here, the other r cancels from the other side, that the friction force, we can actually know what it is now, is equal to 1/2 mass times, I think everything cancels out, it's just acceleration, right? And then you plug it back into this equation. Okay, so what was FB? So FB was I, losing a little bit of space here. So FB was equal to I times the length of the rod multiplied by the magnetic force. Okay, and we have to subtract from that the friction force. Well, the friction force we just said was 1/2 mass times acceleration, and that's equal to also mass times acceleration. So now we can simplify this and say IdB is equal to, what is this going to be? It's 1 minus 1/2, or 1 plus 1/2, I should say, sorry. So you end up getting 3/2, right? MA. And then we can solve for A, right? So now A is equal to 2IdB divided by 3M. You'll notice that there's some pretty big similarities to what we've done before. You see the same kind of features in this equation as exist in this equation, but there's two things missing, right? There's the 4 and the L. Where do those come from? They come from the kinematic equations. The kinematic equations say initial velocity is 0, final velocity is what we're trying to calculate. We know what the acceleration is, and we also know that delta x is equal to the length L, okay? So now we just use one of our kinematic equations, the one that says that final velocity squared should be equal to initial velocity squared, but the initial velocity is 0, right? Multiplied by, or plus 2 times a times delta x. And that gives us everything we need. I'm sorry, not with a square root sign. So if it's vf squared on the left side, it's just going to be 2a delta x, right? I don't know, you probably see it already. You get the exact same answer. So v final ends up being equal to the square root of 2 times a. Well, there's a right there. So 2 times 2 idb divided by 3m, and then multiplied by the thing that I left out before, which was delta x. And look, that's exactly the same equation, right? So it's weird, right? Your question was, we didn't account for friction, but look, we actually did. It turns out that by doing this, we technically accounted for the work done by friction. Now, there's another important point about this that's really important here, because you could ask the question, like, well, what about the friction force? I mean, certainly the friction force is doing work, right? Certainly it's pulling energy out of the system, and you wouldn't be wrong, but it's in a different way than you might expect. So I would ask this question, is this friction force, is it static or is it kinetic friction? Does that question make sense? Is this static or is it kinetic friction? It's just for that point. Exactly. You guys understand. You must have had a very good 1A teacher. You guys probably had Goldman. So yeah, it's static because this point is effectively at rest relative to the bottom surface. And as a result, this object, it's static friction. And static friction doesn't actually do work, right? Because the object isn't sliding along the surface. Now, there is going to be some energy loss due to friction. And I would say this is the ideal velocity that you would get. And the real velocity would probably be a little bit smaller because there's things that are happening here that we're not taking into account for, which is that if you have a metal on top of a metal and it's rolling, you can imagine there's a lot of sound generated. There may even be sparks that are generated, considering, like, how did you actually produce the current right here, right? Like, I don't see any wires in this picture, right? We're completely ignoring those things. We just say, oh, we have a current here. But in reality, you're going to need to have some connection on both sides that maintains in order to keep this current going. In fact, maybe what you do is you apply a positive voltage to this side and you apply negative voltage to this side over here and you get the current going. But either way, there is friction. It's just that the friction isn't going to do any work, so to speak. Okay, so there we go. You guys have any other questions? That was a very good question, by the way. Why friction being neglected? Because I like to be able to show that this stuff, it's all in there. It's just, yep. Right on. Okay, let's take a break. Probably till 3:25, I would say. We might only do one break, so maybe we go to 3:30. We'll take a longer break here, and then we'll have the second half will be a little bit longer. So let's take a break till 3:30. Wow, that's 18 minutes. That's a long time. Okay, we went kind of over though, and if we're only going to take one. And I will stop the recording.